My name is Toby O'Gene. I'm a soil resource specialist in Cooperative Extension in the Department of Land, Air, and Water Resources. And today I'm going to share with you a group project that we recently started, which is trying to use soil survey data to understand how agricultural landscapes can capture floodwaters and promote groundwater recharge. California relies heavily on groundwater to supplement its industrial, agricultural, and municipal needs. In times of drought, we utilize upwards of 50% of groundwater resources compared to considering our overall demand. And in periods of excess water, we can use as little as 20%. So that demand is changing through time, and also groundwater recharge changes through time. In drought, obviously, we often overdraft our groundwater bank, and in periods of excess rain, we are frequently recharging groundwater supply. And unfortunately, demand and recharge do not coincide. And with increasing climatic uncertainty, we need to understand ways that we can capture water and get it into our groundwater supply as our crutch in instances that can promote a more secure water supply. And so this project attempts to identify what soil and agricultural landscapes can be used to capture water at the few times when it is most available or unaccounted for by other users, and that's during flood events. Can we actually capture and divert floodwaters and apply that on the vast acreages of land to promote groundwater recharge? And so, as you can imagine, not all cropping systems and soils are best suited for this practice. And so this is the objective of our project. We're going to try to identify what types of soils are suitable for water recharge. And these soils are very diverse in the Central Valley and in other parts, agricultural regions in California. We have soils that have hard pans, clay pans, and layered soil profiles throughout the valley, which, as you can imagine, might impede the vertical percolation of water. And in contrast, we have homogeneous soils. Some of those might be coarse textured and can rapidly accommodate groundwater recharge. Others might be fine textured and may be slowly permeable to water percolation. And so we need to understand that soil variability. And fortunately, we have soil survey to help us understand that variability, and it is a systematic variability. Soil survey is the most comprehensive geospatial database in the United States. It documents how soils change across the U.S. and specifically in California. And this, as I mentioned, is a systematic variation. And in California, you can kind of get a glimpse of that systematic variability by looking at this map. You can see that in the areas of the eastern edge of the San Joaquin Valley here, we have these orange and red colors. These are old soils, remnant terraces that have cemented layers and clay pans that might not be ideal for groundwater recharge. In contrast, we have the west side of this Great Valley, which is fine textured and maybe slowly permeable to water. So that too might not be an ideal scenario for vertical percolation of water. The center of the valley oftentimes has a regionally high groundwater level, and that might limit its capabilities to accommodate water. We have in green these recent alluvial fans. They're approximately from present to 18,000 years in age. These are bodies of homogeneous, oftentimes coarse textured sediment that could rapidly accommodate groundwater recharge if water were applied to them in the right amounts. And so there are these systematic variations in soils, and the potential areas that we're most interested in are these alluvial fans, these massive fans that have been sourced from the high Sierras along floodwater river channels from the Cosumnes, possibly McCollum, Stanislaus, Tuolumne, Kern, other major rivers that enter the valley. So our goal is to utilize the soil survey database, the digital soil survey data, and repackage it in creative ways to make maps of the soil's ability to accommodate deep percolation and groundwater recharge in these unique events where we might be able to capture water during flood events and route that water onto agricultural landscapes. And so we're not just considering how permeable the soils are. That's only one part of the decision. We also want to consider how standing water or saturated conditions might influence a crop that is associated with that soil landscape. So we want to understand how long water might reside in the rooting zone. We also want to understand if there are chemical limitations, such as excess salinity in the soil, which might be flushed down into the groundwater, further contaminating certain areas. We want to consider the surface condition of the soil. Is allocating large amounts of water going to promote soil erosion or destroy the health of the soil in some ways? We also want to consider slope. Obviously, flat land is going to best accommodate applications of water. The Soil Agricultural Groundwater Banking Index is essentially a combination of these factors. We've looked at surface condition, which is essentially the susceptibility of the soil to aggregate destruction and erodibility. We're considering chemical limitations, such as salinity. We have two hydrological conditions that we query from the soil database. The ability of the soil to accommodate deep percolation, and that is just the lowest saturated hydraulic conductivity or layer in the soil, or the soil with the lowest permeability might be a better way of describing it. The soil layer with the lowest permeability. The other hydrological consideration is the root zone residence time, and that is an aggregate assumption, or not assumption, but estimate of the texture of the soil relative to, or how freely drained that root zone is. To get at the question of, well, if we add water, how long are saturated conditions going to maintain themselves in the root zone, and what effect might that have on certain crops that are grown in the valley, specifically tree crops, which have very high value. And so when some trees are subjected to saturation, they become more prone to disease. So we want to be careful of that. And the other aspect of information that we're going to use is slope. And obviously, steep slopes are going to be less ideal, gentle slopes more ideal for this practice. And so we take these values that we're querying from Soil Survey and we rate them using these graphs located down here. And this is just some example graphs. These are fuzzy logic rating systems, and they're relatively simple. The values of the different factors I mentioned above are listed on the x-axis. Here's an example of saturated hydraulic conductivity. And you simply give that value, say a value of 20, a score by reading up across a graph and over to this numerical rating system, which varies from 1 to 0. And so this is an example of a more is better curve. The higher the permeability, the better that soil should rate for deep percolation. Another example of this type of rating mechanism is an optimum / less is better rating curve. And this would be a curve that we might apply for salinity. We don't want excess salts being leached into our groundwater supply. So as EC, electrical conductivity, increases, salinity increases. And so there are threshold values that would be fine, but once we go beyond that threshold value, the situation might get worse, exponentially worse, or linearly worse. And so this curve is an example of less is better, meaning the lower the electrical conductivity, the better the score. And so these factors, these rating systems were used for all the factors, and then we sum them up to get our suitability index, which we call SAGBI. So this is an example of some of the output that we get from our model. This is a legend here that we might consider if we turn those scores into a percentage from 10% to 100%. The graph and the map in the top, figure A, shows deep percolation, the distribution of this factor across the state. You can see that there are not many scenarios in the state where we have ideal permeable soils to accommodate this practice. Map B is a map of the factor of root zone residence time. And you can see here we see a systematic pattern where the eastern half of the valley seems best for maintaining a freely zoned root zone, or a freely drained root zone. Map C is showing you the factor of salinity, and you see here that the west side of the valley in general might be less suited for this practice of groundwater banking because of the excess salinity levels associated with the west side soils. The rest of the state is ideal for this consideration. And then map D shows the distribution of surface condition. This is essentially reflecting how these soils might respond to receiving a large allocation of water. Are they resistant to erosion and or destruction of surface aggregates? And you can see here that generally the center of the valley is going to be problematic. It's the soils that have lots of silt particles and fine sands that are most prone to a destruction of the surface condition and therefore more susceptible to erosion. And so this distribution of factors gives us confidence that we chose the right factors. They're not overlapping in trends, and this means that we picked out meaningful factors to reflect our integrated index. And so in general, we're happy with the way these each lay out. And when you combine them, this is the overall soil agricultural groundwater banking index map. And you can see that we've grouped values based on some categories that we call excellent, good, moderately poor, poor, and very poor. And you'll see that there are not a lot of opportunities at first glance. And our hypothesis, original hypothesis that I outlined earlier, that these large alluvial fans that are supplying sediment from the major river drainage networks might be our best locations to accommodate groundwater recharge. These are the sandy soils that are homogeneous. They don't have restrictive horizons, they don't have excess salinity, and they're not prone to erosion. So that's why they're rating so high. And they're located essentially in patches along the east side of the San Joaquin Valley. There are some in the west side area, but they're much smaller in spatial extent. We also have a large zone in the southern part of the valley that has a lot of good and excellent land for this practice. So when considering moderately good through excellent, you can see that a little less than 35% of the soils rate as suitable, potentially suitable for this practice. And that corresponds to a little over 4.5 million acres of land. So there's a lot of land. But we really need that number to be very, very high because, as I mentioned or alluded to earlier, certain cropping systems are intolerant or will be intolerant of this practice. And so we need to maximize the amount of land that might be suitable for this potential land use practice. Moreover, the more land that we have that is suitable, the less water that we might need to apply. And that's obviously important in terms of the risk to crops. So one thing that this index didn't account for is that soils have changed through time, and our soil surveys have not been able to document that change. And that's because our soil surveys are relatively old. Most of our surveys in the Central Valley were developed and produced about 40 to 50 years ago. And soils have been extensively modified after that fact. And that's largely due to the expansion of tree crops in the Central Valley. Tree crops, standard practice for tree crops and vine crops is to deep rip or deep till soils prior to planting. That removes the offending soil layers that impede root penetration and also impede deep percolation of water. So lots of soils where tree crops and grapes have been planted have been modified by this practice, making them much more permeable than what soil survey currently documents. And so what we had to do was update soil survey to account for this change. And by doing this, or how we did this, is that we made a map of soils with restrictive layers, clay pans or cemented horizons, and we overlaid that map with imagery showing where tree crops are currently planted. And that combination of presence of tree crops and soils with restrictive horizons, we then modified so that those soils are now not being considered. They are being considered in the index, but the limiting layer has been removed from the data set so that now that soil behaves more in a more permeable manner than it did prior to this database modification. So this is an example of the Soil Agricultural Groundwater Banking Index. When we account for deep tillage, we've updated soil survey to document this change. And what you can see is we have much more land area, an expansion of the soils that might be suitable for this groundwater banking process. You can see that now we're approaching 55% of the soils that might be suitable for groundwater banking, and that corresponds to about 7.5 million acres of land. And so we've dramatically increased that area just by simply updating soil survey where it was incorrectly reporting information. Not incorrectly, just not current. And so we're happy with this outcome. It gives us a lot more opportunity to evaluate the relationships between soils that might be good for this practice and certain crops that are tolerant of groundwater banking or experiencing saturated conditions. And so that's what we're headed or working on right now, is we're trying to understand the spatial extent of key crops in the Central Valley and other agricultural valleys to get an idea of what soils, combination of soils and cropping systems are best suited for this practice. We need to consider crops that might be vulnerable to standing water and disease, high-value crops especially. So we also need to consider crops that have high demand for nitrogen. As you might be aware, a lot of our agricultural groundwater supply is contaminated with nitrate, and we don't want to exacerbate that contamination level by leaching soils that are rich in nitrogen. The problem is we don't have great spatial coverages of current land use. The Department of Water Resources has great files that document land use cover across the agricultural regions of the state, but they're a little bit out of date. It's difficult to maintain this for every county, and so because land use changes so quickly, we're not getting the most up-to-date piece of information, but it's better than nothing, and so we hope to incorporate that information in our model. We also wanted to get a feeling for how our most valuable crops might respond to saturated conditions in the springtime during flood waters or episodic flood events. And so we sent out a questionnaire to Cooperative Extension farm advisors who specialize in tree, crops, and vines. And we asked them questions about how they felt about a specific crop's tolerance to standing water or saturated conditions. And you can see in this table here, we asked experts to rate a crop tolerance, 0 being not tolerant, 4 being highly tolerant, and maybe in excess of 2 weeks of standing water or 2 weeks of saturated conditions. And so we asked them to rate that tolerance prior to bud break and then after bud break. And what you see here is that, first of all, there are several crops that are intolerant of water. And also some of those crops are those that occupy vast acreages. Almonds, for example, is probably the most expansive, our largest spatial extent in the Central Valley. And under certain root stocks, this is completely intolerant of standing water, or very close to that, only 48 hours it can withstand. In contrast, almonds on a different rootstock, a plum hybrid, might be much more tolerant to standing water, particularly after bud break. And so there are opportunities. The disadvantage is that these almonds are planted in areas that are poorly drained and therefore might not be the best candidates for agricultural groundwater banking, whereas these almonds are typically planted in our well-drained locations and probably are going to be less tolerant of standing water. You can see citrus is intolerant also, avocados too. The success, one potential encouraging outcome is that wine grapes are very tolerant of standing water prior to bud break, and that occupies a substantial amount of land in the Central Valley and other areas, agriculture areas in the state. So that's encouraging. And so we hope to use this information in our final product. Our final product is going to be converting these maps to an interactive decision support tool. This support tool will look like a map, but it'll be able to, the users can interface that map in Google Earth or Google Maps. They could enter a location in a screen, and it would zoom to that location, and they could query the landscape so that they could not only get the sustainability or the index value, but also it would be portrayed in a transparent manner so that we could see how each factor rates to identify the limitations. And we would also blend in our understanding, or our growing understanding, of how certain cropping systems might behave relative to the different ratings that we see here below. So this is an opportunity just to promote the functionality of the tool in the near future. So there's a lot of questions that still arise. We have certainly not solved the problem of where to bank water in agricultural landscapes. We've certainly just scratched the surface. The next question that we need to answer is, what does agricultural groundwater banking actually look like? How much is too much? Obviously, we don't want a scenario like this where we're adding so much water that it would be catastrophic. Could it be as little as just maybe 1 or 2 more irrigations a year during the springtime? So that's where we think this research is going to lead us, is that this is the starting point, so we can actually understand how little water could we actually apply over broad landscapes or areas to maximize the impact statewide. There are a variety of other questions we need to work out. We really do need to spend more attention on understanding what crops are most appropriate for this, which crops are just too valuable to take this risk, are too susceptible to disease if they experience standing water, which crops require agricultural chemicals and levels high enough that we just don't want to take the risk of flushing those soils heavily at those times of the year for the purposes of banking groundwater. We want to, in general, understand the potential for contamination, both from a cropping system perspective, but also many of our soils have legacy levels of nitrate, and not necessarily soils, but vadosone, the material below the soil profile, but not within the groundwater, has been shown to have high levels of nitrate in the sediment solution. And if we are now applying large amounts of water to that landscape, what's the risk of flushing that legacy nitrogen into the groundwater supply? We need to address concerns of growers. This might simply be too much of a risk for growers, or the timing might be inappropriate for some of their cultivation practices. So we need to get their feedback considering when are the opportune times, and do those opportune times match when water might be available. We need people to start working on incentives for growers to consider this management practice. There's considerable risk with applying a large amount of water to your agricultural landscape, and we want that risk to be minimized at all possible. And so are there insurance policies that we could investigate? Are there cash rewards for implementing this practice? All those complicated decisions and opportunities need to be thought out in the policy arena. And then finally, there are probably many existing barriers to this practice that we haven't thought of yet. And so all of this needs to come to the forefront in future discussions. Thank you.